Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of cryogenic engineering. I will just briefly take an overview of what my earlier lectures were. In the first lecture, we talked about what is cryogenics, and we discussed various applications of cryogenics in space, in superconducting, in mechanical engineering, and in medicine and things like that. In the last lecture, which was the second lecture, we talked about different temperature scales, and we also concluded from there that one can positively use Kelvin scale. It is for our benefit. We do not have to say every time minus 196 degrees centigrade, and we can always say 77 Kelvin using this temperature scale. We also talked about various cryogens. We talked about their properties, and we talked about the importance of TS diagram, that is temperature entropy diagram. We found that from the temperature entropy diagram, a lot of things can be understood. We can understand what is the boiling point, what is the critical point, how the enthalpies vary with temperature, how the entropy vary, and how different pressures and temperatures vary. And we discussed different cryogens and their properties in brief of argon, air, nitrogen and neon. So, here we got a feel of various cryogens, and what I am going to talk about today is cryogen hydrogen. We talked about speciality of hydrogen, that is ortho and para forms of hydrogen. What are these different forms? What is it all about? We will see in this lecture. Then helium is a very special gas, is a very useful gas in cryogenic engineering, and we will discuss the phase diagram of helium. What are different phases in helium, how do they coexist and things like that. In my last lecture, when I talked about cryogen, we had written one statement over there that hydrogen and helium are special cryogens, and therefore, they will be dealt specially in a special lecture, and this is the special lecture which we are going to talk about hydrogen and helium, and in fact, we will continue about talking about helium in the next lecture also. Let us go up to hydrogen, which has got its boiling point of 20 Kelvin. Hydrogen exists in diatomic form as hydrogen, everybody knows about this, and these are the normal properties of hydrogen gas. What are its properties? It has got a normal boiling point of 20.27 Kelvin at 1 bar, 1 atmosphere. It has a normal freezing point of 13.95 Kelvin. It has a critical pressure of 1.315 MPa or around 13 bar pressure. It has a critical temperature of 33 Kelvin, 33.19 Kelvin to be exact. Now, it has got a density of 70.79 kg per meter cube, and the latent heat is 443 kilojoule per kg when it gets converted from gas to liquid or from liquid to gas. These are very important properties, and this means that I can use liquid hydrogen to give me cooling effect at 20 Kelvin, around 20 Kelvin approximately or above. I cannot come below 20 Kelvin. If I were to come and use hydrogen at lower temperature than 20 Kelvin, then I have to remove the pressure over it. That means, I have to go into vacuum to touch down lower and lower temperature. And at 13 Kelvin, 13.95 Kelvin, liquid hydrogen will get converted to solid hydrogen. Now, this is the temperature entropy diagram of hydrogen. I always told you that all the mechanical engineer or all the cryogenic engineer first should refer to TS diagram to understand the different property variations with temperature. So, on the y axis what we have is a temperature, and what x axis what you have got is a entropy. You may not be able to see properly, it is possible, but just have a look at different lines on this diagram. For example, you can see the dome over here. It means that inside this dome what you have is a two phase mixture, that is liquid plus vapor. You can see all these lines which are coming from top to bottom. It means they are all isobaric line, that is the pressure remaining constant, and you can see all these curved lines, they are all isenthalpic line or the enthalpy remaining constant. Why I am stressing this point is, when you go in the next lectures, when you go for liquefier and refrigeration, we will deal with these diagrams in every problem. We have to understand the property variation, enthalpy variation, entropy variation at every point, and for that we will always have to refer to the TS diagram of different gases or different cryogens. So, here you can see a line which is at 1 bar, and this is the temperature corresponding to the change of phase from gas to liquid, or nothing but the boiling point of hydrogen, which is 1 atmosphere pressure and 20.27 Kelvin as the temperature. Now, this is the critical point, and the properties of critical point are 13.15 atmosphere and 33.19 Kelvin temperature. So, this is the critical temperature and this is the critical pressure. In addition to that, I have just given data to understand the density of vapor at 1 atmosphere in the saturated condition is 1.33 kg per meter cube, and that of liquid is 70.79 kg per meter cube hydrogen. Now, some general information about hydrogen. It has 3 isotopes: hydrogen, deuterium and tritium. Now, the relative percentage of existence of these 3 isotopes is 6400 to 1 for hydrogen and deuterium respectively. The atomic mass in this case, all these things have got 1 proton in the nucleus, and the number of neutrons will vary depending on what isotope we are talking about. For example, for hydrogen we have got 0 neutron, for deuterium we have got 1 neutron, and for tritium what we have is a 2 neutron. Now, this tritium is very rare substance, a very rare gas in comparison to what you see for hydrogen and deuterium. In addition to that, the tritium gas is a radioactive gas and is unstable with a half life of 12.5 years. So, whenever we have to deal with tritium, one has to be very careful, one has to worry about all its radioactivity, and all the measures have to be taken to deal with this tritium. In fact, this is not normally used in commercial operations. What normally we will use is hydrogen, of course, and sometimes we can have deuterium as heavy water, etc. We will come to that later. The relative ratio of existence of hydrogen as diatomic molecule, that is hydrogen H2, and as hydrogen deuteride. Sometimes hydrogen is like H2 or HD. Deuterium atom get combined to form hydrogen deuteride HD, and the relative ratio is 3200 to 1. Now, the important part about hydrogen is it exists in 2 molecular forms, that is ortho and para. So, we have got an ortho form and we have got a para form. This is very important, and we will talk about these ortho and para forms of hydrogen in little bit details in the coming slides. So, what is this ortho and para hydrogen? Well, before I really go into ortho and para etc., I will talk about some third parameter called spin, because from this definition of spin we understand what is ortho hydrogen and what is para hydrogen. So, what is the spin? The spin is defined as a rotation of a body about its own axis. We know the earth spins, we know a top, while on the earth when it rotates, it spins about its own axis, all right. So, this is what I am talking about, one hydrogen molecule, and you got 2 atoms of hydrogen together, which means you got 2 protons, okay. So, hydrogen molecule has 2 protons and 2 electrons, all right. These protons will be spinning all the time. The distinction between the 2 forms of hydrogen, what we talked about as ortho hydrogen and para hydrogen, is basically because of the direction of the spin of these protons. So, as I just said, these 2 protons will have some spin, and what is the direction of that spin will decide if it is a ortho hydrogen or if it is a para hydrogen. As soon as we talk about ortho and para, lot of properties associated with the energy of hydrogen will get decided, and we will talk about that in the next slide. The 2 protons possess a spin which gives angular momentum. Possibly I talked about this in MRI system also. You got hydrogen molecule, and this proton immediately gets aligned to the magnetic field because of this spin. Similarly, I am talking the same thing here. The 2 proton possess a spin, and this gives an angular momentum which will have a direction. So, here you can see 2 protons, and you can see 2 clockwise directions over here which indicate the spin of these protons. If the nuclear spins are in same direction for both the protons, what we call is it is a ortho hydrogen. That means, if both of them are in the same direction clockwise in this case, this is nothing but ortho hydrogen. Okay. And if we see the next slide, we have got 2 protons, 2 atoms hydrogen together. One has a spin in this direction, one has a spin in the opposite direction. So, one is a clockwise and other one is a anti-clockwise, and this is what we call as a para hydrogen. So, essentially if the nuclear spins are in the opposite direction for both the protons, it is para-hydrogen. Both the spins are in the same direction, we call it orthohydrogen, and when both the spins are in opposite direction, we call it a para-hydrogen. So, it is just a difference of spin of the protons which make it ortho or para. Now, what happens? Why are we studying all this? As soon as you start lowering the temperature of hydrogen gas, this ortho will start getting converted to para. That means, the molecules which had the spin in the same direction will now have spins in opposite direction. So, with the decrease in the temperature, the orthohydrogen is getting converted to para-hydrogen. So, what is happening as you lower the temperature, the gas hydrogen will slowly start getting converted to liquid. And here, when we start lowering the temperature or when we start liquefying the gas, basically I want to reach down to 20 Kelvin from room temperature, what will happen? Orthohydrogen will get converted to para-hydrogen. And how do they happen? What is the percentages of ortho and para? Is at 300 Kelvin, I got 75% ortho and I got 25% para. All right. And at 20 Kelvin, after the whole conversion has taken place and equilibrium hydrogen has formed, what I have is all the ortho, almost all the ortho have got converted to para. So, para-hydrogen at 20 Kelvin, which is nothing but the boiling point of hydrogen, the 75-25 ratio has got converted to almost 100%. 0.179 ortho has remained there, while para is 99.8% here. So, almost 100% ortho has got converted to para. All right. Now, this is the clear distinction what exactly happens when you go on lowering the temperature of the gas from 300 Kelvin to 20 Kelvin. Here ortho gets converted to para. Now, this para form is a low energy form and therefore, heat is liberated during conversion. This is a very important thing, that ortho has got higher energy form while para is a low energy form. So, during this conversion, the heat is liberated because ortho has higher energy while para has lower energy. So, during this transformation from ortho to para, lot of heat gets liberated, which means that this is basically exothermic reaction. So, conversion of ortho to para as one goes on lowering the temperature is basically going to result in the release of energy, or there is a lot of heat energy is involved over there. So, conversion of ortho to para form of hydrogen is an exothermic reaction, and this conversion is a very slow process. This is the most important point again about this conversion. Just want to summarize, as you go on lowering the temperature, 75-25 ortho will get converted to para, which is 0.179 and 99.8% respectively. This process of ortho to para conversion is a exothermic reaction, and also this conversion is a very slow process. It does not happen fast, it happens very slow. It is very important for liquefaction that this ortho to para conversion takes place faster, and it is also very important that this conversion is complete during liquefaction. What will happen? We will see later. But if I want to make this process of conversion very fast, then what I have to do is I have to add catalyst to this reaction. So, in order to make this conversion faster, catalysts are added. There are different kinds of catalysts, there are 3 or 4 types. They have to add it in correct quantity in order to convert the ortho hydrogen to para hydrogen as fast as possible, or to make the reaction faster. So, I just said during liquefaction, the heat of conversion causes evaporation of 70% of hydrogen originally liquefied. Now, this is the effect of this conversion from ortho to para. What is happening during liquefaction? The temperature is decreasing. What is happening because of the decrease in temperature? The heat of conversion is getting evolved, that is, it is being an exothermic reaction, lot of heat is being liberated and it evaporates. Because of the effect of this heat release, whatever liquid has got formed, it gets evaporated immediately. So, if I get liquid, 70% of that liquid will get evaporated because of this conversion from ortho to para, all right. And this is very important constraint in liquefaction and storage of hydrogen. So, as I said, the conversion is a very slow process, and if the conversion does not take place during liquefaction, I will store in the form of liquid. In this liquid form, this ortho will slowly get converted to para. During this conversion from ortho to para, lot of heat will get released and therefore, lot of liquid will get evaporated. It means that we should ensure that during liquefaction, all the conversion happen. All the conversion happens during liquefaction only. That means, all the conversion from ortho hydrogen to para hydrogen happens during liquefaction only. If that does not happen, then whatever liquid you get at the end of liquefaction, the ortho will get converted to para in the liquid form and therefore, it will cause the evaporation of most of the liquid that is stored. And this is very, very typical of hydrogen. This has to be taken care of. So, what we do? We add catalyst during liquefaction. As I just said, the catalyst make this reaction faster and this will ensure that the whole conversion of ortho to para will take place during liquefaction only and whatever liquid has got formed, it will not get then evaporated. Now, this is a graph which shows that depending on the initial ortho existence in the liquid, how much amount of liquid will remain at the end of so much of storage time. For example, this talks about mass fraction remaining in ortho to para conversion progress and this is the storage time on the x axis. If I talk about this line for example, I have got liquid and this liquid has got 60% ortho. That means, the whole conversion has not taken place during liquefaction. The liquid which I have got is stored with 60% ortho in it. What does it mean? That after so many hours, more than let us say around 1500 hours, what remains here is only 0.35%. Okay? Whatever original was there, only 35% of that remains, all the rest is getting evaporated. That means, around 65% of the fluid has got evaporated completely. However, if I compare this with this figure of 20, that means, my liquid hydrogen which I have got had only 20% of ortho remaining in it. That means, 80% conversion had taken place. Okay? It has got 20% ortho in it. At the end of around 1500 hours, what it will have is around 70%. That means, only 30% liquid has got evaporated during the conversion when the initial ortho existence was only about 20%. Now, imagine if I got all the conversion taken place during liquefaction, that means, my line would almost be flat line over here. If I just extrapolate this, if I say that all the conversion has taken place during liquefaction only, then over 1500 hours, this line possibly could have been at 95%. That means, only 5% possibly would have got evaporated. This shows the importance that the liquid hydrogen which I am storing should have no ortho content or as little ortho content as possible. It means that all the ortho which was there should get converted into para and therefore, all the ortho to para exothermic reaction would take place during liquefaction only. So, this figure shows the fraction of liquid hydrogen evaporated due to ortho to para conversion with storage time. This is very important and a big difference of hydrogen as compared to all other cryogens. Hence, we should ensure that liquefaction of hydrogen should ensure complete conversion. This is what I talked about. I am sure this is clear to you. The second gas or the isotope of hydrogen is deuterium. It has got one proton and one neutron and two deuterium atoms make one D2 which is called heavy hydrogen. So, you know D2O is heavy water and D2 is what we call as heavy hydrogen. Now, similar to hydrogen, deuterium has got also ortho and para forms, but they are in different forms. That means, their percentages are different. The relative concentration of these two forms is a function of temperature again as what it is in normal hydrogen. The normal deuterium has got 2/3 ortho and 1/3 para. So, 66% is in ortho and 33% in para at initial case as against 75-25 over there. As the temperature decreases for deuterium, here the para D2 gets converted to ortho D2 as against ortho H2 get converted to para H2. So, it is opposite that. Alright. This is just a point for comparison. We are not going to talk about deuterium in detail, but I just wanted to show the comparison of deuterium behavior with that of hydrogen. So, what happens at 300 Kelvin, you got 66.67 ortho and 33.33% of para. At 20 Kelvin, that means, when the whole thing has got converted to liquid deuterium, what you have is almost all the para has got converted to ortho. So, you got 98% ortho and 1.998% para. This is the point of difference between deuterium and hydrogen. Most of the physical properties of hydrogen and deuterium mildly depend on ortho and para composition. So, whatever be composition, the physical properties do not depend so strongly on this ortho and para conversion. The different uses of hydrogen we have talked about. It is used in cryogenic engine as a propellant, as a fuel. It is being considered as a fuel for automobile. This is very important. Liquid hydrogen as a fuel is a very popular, and it is looked at as a fuel, future fuel bypassing petrol and diesel. Cryocoolers working on a closed cycle sometimes use hydrogen as a working fluid. However, one should know that hydrogen has got some safety requirements. Hydrogen codes and standards should be followed to ensure safety while handling liquid hydrogen. These are different uses of hydrogen. The next gas is helium. As I have explained to you about helium, this is one of the very important gases as far as cryogenic engineering is considered. Why? Because it is an inert gas, it is a non-reactive gas, and it has got the lowest possible boiling point, it is 4.2 Kelvin at 1 atmosphere. It means that this gas will remain in gaseous condition till 4.2 Kelvin. All other gases will get liquefied because their boiling points are above 4.2 Kelvin temperature, and therefore, if I want to achieve temperatures very close to 4.2 Kelvin or below or in the range between let us say 50 Kelvin to 4.2 Kelvin, I got no other option, but the only safe gas, the inert gas is helium. Helium has got a tremendous importance in cryogenic engineering. The evidence of helium was first noted by Janssen during solar eclipse in 1868. It was discovered as a new line in the solar spectrum. So, the discovery of the gas only happened around 1868. In the year 1895, Ramsay discovered helium in uranium mineral called as clovite. So, this was discovery on the earth for the first time in 1895. So, you can understand that it is a gas of just 115 years old on the earth since invention. In the year 1908, Kamerlingh Onnes at Leiden University, his liquefied helium using helium gas, which he obtained by heating monazite sand procured from India. So, this is a Indian connection to the first helium liquefaction that happened in 1908 by Kamerlingh Onnes at Leiden University in Netherlands. All right, this is a good Indian connection of which I talked about earlier, and also I told you about in year 2008 what we had is a centenary year of helium liquefaction. So, all the cryogenic engineers and physicists associated with low temperature research celebrated the year 2008 as a centenary year of helium liquefaction. Helium is an inert gas and exists in monoatomic state. These are the properties of normal helium. What are they? It has got a boiling point of 4.25 Kelvin. Normal freezing point, it does not exist. Critical pressure, it has got 0.227 MPa, that is around 2.27 bar. Critical temperature 5.25 Kelvin. Liquid helium density is 124.8 kg per meter cube, and the latent heat is around 20 kilojoule per kg, 20.28 kilojoule per kg. It is a very small latent heat. It means that with the smallest heat coming, the liquid helium will get evaporated, and so one has to be very careful in the usage of helium. Heat in leaks that happen when you use liquid helium. It is a very important parameter, because the latent heat is the one which gives you the amount of cooling effect or refrigeration effect what you want at 4.2 Kelvin. Let us see the same properties on a TS diagram for helium. Here you can see the dome, and this is 5 Kelvin, which means that 5.2 is a critical point over here. And what you can see is again the pressure lines, enthalpy lines, and there are density lines also. On the x axis what you have is entropy. This is a 1 bar line. What you see is a boiling point of helium, which is 1 atmosphere and 4.2 Kelvin. This is the critical point, and the critical coordinates are 2.27 atmosphere and 5.25 Kelvin. This information has to be known by all the cryogenic engineers. So, whenever I say helium or hydrogen or nitrogen, one has to know the boiling points one has to know what are the critical parameters associated with those cryogens. This is the least expected from a cryogenic engineer, because the choice of temperature, the choice of pressure one has to have this knowledge when we apply these cryogens for a specific application. Again, the density for comparison sake, the density of vapor at 1 atmosphere in saturated condition for helium is 16.87 kg per meter cube, and for liquid it is 124.8 kg per meter cube. Helium in 1920, Aston discovered another isotope of helium, which is helium-3 in addition to helium-4. Now, this isotope of helium, which is helium-3, is also very important in cryogenics, because this is what we use in dilution refrigerator in order to reach temperatures below 1 Kelvin, and therefore, this aspect will be covered in the next lecture, and this is a very important, and its discovery happened in 1920. Helium exists at 2 isotopes, helium-4 which has got 2 protons and 2 neutrons, and helium-3 what we just talked about as 2 protons and 1 neutron, and that is why we call it helium-3 and helium-4 respectively. The percentage of helium-3 is very, very small, 1.3 into 10 to the power minus 4%. So, mostly whenever we get helium gas, it is helium-4 only. All right. So, these terminologies are used quite frequently in helium, which is helium-4 and helium-3, and in further we find helium-1 and helium-2. These are very different ways of putting helium in very different contexts. So, one has to get used to talking helium-4 and helium-3. When I say helium-4, it is a normal helium. When I say helium-3, it is the isotope of helium-4. So, the isotope is helium-4, which is relative percentage wise almost 100% is helium-4. Of course, there is helium-3 and the relative percentage is very small. This also means that the cost of helium-3 is very, very high as compared to helium-4. I will not be able to tell you exact cost of helium-3, because we could never buy that in India. However, this cost will be possibly 100 times more than that of helium-4. So, it is a very costly, and therefore, its usage has to be really properly justified. Now, what is important about helium is its phase diagram. This is the one of the most important aspect of helium. Okay. Try to understand this, because I am going slow and trying to explain as much as I can on this diagram. If I want to understand about helium phase diagram, what I have is a pressure and temperature. Okay. I am plotting pressure and temperature here, and what you see is a saturated vapor pressure line basically. So, at 5.25 Kelvin, what you have is a critical temperature. Corresponding to that, what the pressure would be? Critical pressure. So, you got a critical pressure and critical temperature. Below this would be what we get is a 2 phase, that means liquid and vapor. As you know from the TS diagram, under the critical temperature and pressure is that what you get is the liquid and vapor. So, this is my vapor pressure line, and on this, if I give this point, this is nothing but 4.2 Kelvin and 1 atmosphere, which is a normal boiling temperature of helium. So, what you have here is a vapor, and what you have this as a critical point, and here comes a different line, which is nothing but solid hydrogen. What you have is a liquid helium over here. Okay. So, now you can see that I got 3 phases. I got liquid helium over here, I got vapor helium over here, and what I have here is a solid helium. It means that the liquid and vapor are coexisting together, solid and liquid are coexisting together, but the solid, liquid and vapor are not coexisting together. All right, and this is a very important aspect of helium. From the adjacent figure, helium has no temperature and pressure at which solid, liquid, vapor can coexist. It means that it has no triple point, and this is why we say that if you go on reducing the temperature of helium, it will still remain in liquid state. It will not reach the solidification point. Now, there is a lot of physics associated with it. Helium has a very high 0 point energy and things like that. It has got very involved physics, and therefore, I do not want to really go into the details of those physics aspects. For engineers, it is important to understand that helium does not have a triple point as most of other cryogens have. Now, what happens? Of course, solid helium does exist. So, if I want to convert something to solid helium, what I will do? I will have to pressurize this to 25.3 bar to solidify. So, saturated liquid helium must be compressed to 25.3 bar to solidify. So, this point where I can get solid, minimum pressure is 25.3 bar. Now, on this curve you can see that this pressure has not been given in the scale, because this is 1 bar. The pressure associated with this is around 2.5 bar, and this pressure I am talking about is now 25 bar. So, if I really want to get solid helium, I will have to compress the saturated liquid to 25.3 bar in order to get solid helium. Now, as liquid helium is further cooled below a particular temperature, there is a very specific temperature of 2.17 Kelvin, which is over here. So, if I go on cooling this liquid further in this direction, let us say, a new liquid phase, liquid helium 2 emerges out. This is something different what you see as compared to all other cryogens. So, here liquid helium 2 emerges out, and therefore, what I call these two phases as is liquid helium 1 and liquid helium 2, or helium 1 and helium 2. So, I just pointed out to you in the earlier slide, you got different versions of putting helium in, that is helium 3 and helium 4, which are nothing but isotopes. Again I am putting something which is helium 1 and helium 2. Actually, this is liquid helium 1 and liquid helium 2, but in a colloquial language, I will always say helium 1 and helium 2. So, what is helium 2? Helium 2 is a phase of liquid helium which comes into existence when you go on cooling helium 1, and this new phase emerges when you go below 2.17 Kelvin, which is a very specific temperature. So, what is this all we are talking about? The two different liquids now are called liquid helium 1 and liquid helium 2. So, this is clear from this diagram. Now, these liquid phases are distinguished on the basis of viscosity. So, I got some viscosity associated with helium 1 and I got some viscosity associated with helium 2, and on the basis of that I am doing this differentiation. Normally, liquid helium 1 is normally called as normal fluid, all right, and helium 2 is called as superfluid. You possibly must have heard about this, that helium exists in two fluid form, one is a normal fluid and one is a superfluid form. And what is this superfluid form? And this is what you see from this. What I am giving you here is a line which is joining 2.17 Kelvin up to this point, which divides helium 1 and helium 2, all right. This phase separation line is called as lambda line. So, imagine this is a 2.17 Kelvin touching up to this solid liquid line at this point, and this what I call as lambda line, and this point is called as lambda point. So, the point of intersection of phase separation line with saturated line, the intersection of phase separation line which is this, and where it hits the saturated line at this point is what we call as a lambda point. So, this is lambda point. Now, this is a complete phase diagram of helium, and again I summarize. What you have on the right side of this dividing line is helium 1, what you have on the left side of this line is helium 2. Helium 1, liquid helium 1 is called as normal fluid and liquid helium 2 is called as superfluid. The difference is happening as we go on cooling liquid helium 1 below 2.17 Kelvin, depending on what pressure you have. The line which divides these two helium 1 and helium 2 is what we call as lambda line, and the point where this intersect the saturated vapor line is the lambda point, all right. This is very important to understand, and this is very important that a cryogenic engineer is expected to draw this diagram immediately to understand, all right. Liquid helium 2 is called as superfluid because it exhibits properties like zero viscosity. We made a statement earlier that this difference of helium 1 and helium 2 is owing to the viscosity of the liquids. This new phase which emerges as helium 2 from helium 1 is basically because of the viscosity differences between these two fluids. So, helium 2 is called superfluid. It is called superfluid because it exhibits property like zero viscosity. What I am talking about is helium 2 has got very close to zero viscosity, while helium 1 is like a normal fluid, it has got its own viscosity. What does it mean? It will never have effect like pressure drop, friction. It can move in any direction, all right. It is like mercury basically, it can run in any direction, it can run through small little channels, you don't have to really bother about the pressure drops that are happening in helium-2, and this is very important. The other aspect of this, it has a very large thermal conductivity. Now, these two aspects make it very important features of helium-2, low viscosity or zero viscosity, or we also call it zero entropy. As you come down to 0 Kelvin, it has become much more order. See, the most ordered thing is solid. You got all the lattice crystalline structure, you got a very defined position. While in helium, what you have got is liquid helium is a very helium-2 is becoming ordered liquid. It's not solid exactly, but it is as ordered as solid, and therefore what we call is as zero entropy in this case. All right. So, it has got zero viscosity and it has got a very large thermal conductivity. Now, these two aspects are very important of helium-2. In addition to that, it has got very funny properties. See, lot of research is being done on helium-2 to understand the behavior of helium-2. This is called superfluid. Because of its very high thermal conductivity, because of its zero viscosity, it has got different applications. All right. It ensures that all the superconducting accelerators have got magnets. For example, in CERN, all the magnets are cooled at 1.8 Kelvin. 1.8 Kelvin is nothing but superfluid. What does it ensure? It ensures fantastic heat transfer because it has got a very large thermal conductivity. At the same time, it has got zero viscosity. So, whatever cracks are there, whatever ways are there, whatever paths are there, helium-2 will go and occupy the place. It will not worry about the pressure drops happening over there because of absolute minimum or zero viscosity. All right. The other property is this fluid expands on cooling, which is a very funny property. It cannot be well defined, but it is a very funny property of helium-2. Owing to its low viscosity, the fluid below the lambda line, that is liquid helium-2, flows through the narrow slits and channels very rapidly. This is a very important aspect of helium-2, that it can really flow through very narrow slits and channels and within no time. Otherwise, you have to do pumping or something like that. No. What if you got a mixture of helium-1 and helium-2, helium-2 of this mixture will immediately go through a slit or a channel, but helium-1 will not be able to go through. We will find a lot of applications of this in the next lecture, because we have got very specific experiments one can do on helium-1 and helium-2. Because of this property of zero viscosity, helium-2 can flow through narrow slits and channels very, very rapidly. What happens when one goes from helium-1 to helium-2? What actually happens is there is some kind of a phase transformation, which is something called a phase transition. All right. Although one can see that it is only liquid on either side. So, in reality there is no phase transition. That means there is a liquid to liquid phase transition. So, it is a completely different kind of a phase transition in this case. One has to understand what is the physics behind this. Till now, what we have understood is what is a helium phase diagram look like. We also concluded from here that solid, liquid, vapor never touch or never coexist, and also when we cool liquid helium, it has got one more transition happening below the lambda point temperature, which is 2.17 Kelvin, and a new phase emerges called helium-2. Now, what I am going to talk about is what is this transformation or transition of helium-1 into helium-2 is all about. Let us see that in small details. Again, the physics behind this is very, very big, and I am not going to discuss that. What I am going to do is only some important aspects of this phase transition. Now, when I talk about phase transition, we have got a first ordered phase transition and we have got a second order phase transition also. This is the equation which talks about Gibbs free energy. In thermodynamics, for any reaction, what you have is a Gibbs free energy equal to, we got some internal energy E, we got PV, pressure and volume variations here, PV, and then we got a Ts. So, G is equal to E plus PV minus Ts. This is a very standard equation which comes from Gibbs free energy equation. Now, this Gibbs free energy, if I differentiate with respect to pressure, and if I take the first derivative, first order derivative of this at constant temperature, it will give density. So, if I see the variation of Gibbs free energy with respect to pressure at constant temperature and constant mass, that means whenever there is a phase transition happening at constant temperature and at constant mass, what you get is a density. Okay. This is the first order derivative of Gibbs free energy with respect to pressure at constant temperature, it gives density. This density, which is the first order derivative of the Gibbs free energy, undergoes an abrupt change leading to discontinuity. So, whenever this kind of phase transition happen of first order nature, this is the first order derivative of Gibbs free energy. Whenever this happens, the density undergoes an abrupt change leading to a discontinuity called Gibbs first order discontinuity of or first order transition. I am basically going to explain to you what is the first order transition and what is the second order transition. Alright. In this case, which is the first order transition, what you see is whenever the transitions of this nature happens, this happens at constant temperature and the density goes through a abrupt change. That means, if I see the right side density and the left side density, I will get a big discontinuity at a point where this transformation happen, at a temperature where this transformation happens. All right. The density undergoes an abrupt change leading to a discontinuity called Gibbs first order discontinuity, or this transformation is called as first order transition in this case. What are the features of this transition? This transition involve latent heat. So, whenever a phase transition of first order happens, it happens with a involve energy, it involves energy, either the energy is taken in or the energy is given out. The temperature of the system, however, remains constant. All right. What is I am pointing at is such a transition of first order is nothing but from gas to liquid or from solid to liquid. So, whenever you see conversion from liquid to gas, what has gone into it? Latent heat. It is latent heat of conversion. The temperature remains constant, latent heat is get involved and the density changes abruptly. All right. If I see liquid to gas conversion, there is a involvement of latent heat and there is a abrupt increase in density when I go from gas to liquid, or reverse will happen when I go from liquid to gas. And this is what is called as the first order transition, where the phase changes from solid to liquid or from liquid to gas or from gas to liquid and from liquid to solid. All right. This is what I am going to talk about. For example, the first order transition is nothing but solid to liquid or liquid to gaseous transition. The latent heat is absorbed at constant temperature, and these are the features that are involved in the first order transition. Okay. Now, we will see what is the second order transition, and this is what happens in when you get transformation from helium 1 to helium 2. These transitions are continuous in the first order, but exhibit discontinuity in the second order. All right. So, if I differentiate second time now, Gibbs free energy function, if I differentiate with respect to some other parameter 2 times, then I will get discontinuity there, and that is why this is called as second order phase transition. So, the second order derivative of Gibbs free energy with respect to chemical potential, because there is a chemical reaction happening, some kind of reaction is happening and there is a chemical potential associated with that transition. If I differentiate Gibbs free energy, the equation of which I had given earlier, what I will get is the second derivative of this energy is nothing but specific heat. In the first derivative, what I had got was density. In the second order phase transition, what I get is specific heat, and this variation of specific heat in liquid helium is abrupt in this case and possess a discontinuity at the lambda point. So, what we see in helium 1 and helium 2 is the specific heat change drastically, because it is a second order phase transition. All right. In the first order phase transition, what we had was density variation. In the second order derivation, second order phase transition, what we have is specific heat changes, or there is a discontinuity at the lambda point temperature, which is 2.17 Kelvin, and you will see what it happens. So, this figure really gives you what exactly happens at lambda point. You can see on the y axis what I have plotted is a specific heat, on the x axis what you have is the temperature, and you can see here that the specific heat variation is suddenly random at this point, and literally this is an infinite kind of thing. So, there is a big change in specific heat capacity at the temperature of lambda point, which is 2.17 Kelvin. And what can you conclude from the shape of this line? All right. This point is called as lambda point, and why? It is because of the shape of this curve at 2.17. This looks like a Greek letter lambda. A Greek letter lambda denotes the specific variation at the lambda point, where the second order derivative of the Gibbs free function is discontinuous, and this is what discontinuity we are talking about at the lambda point. And this is why this is called as lambda transition. Sometimes there is no energy involved in this lambda transition. As I said in the earlier case, first order transition, what you had was a latent heat conversion. We had gas to liquid conversion, we had liquid to solid conversion, or solid to liquid or liquid to gas, where latent heat is given in or latent heat is taken out. So, there is the addition of heat or removal of heat were involved. In this case, there is no energy involved, there is smooth transition from one phase or one condition to another condition, one liquid helium 1 to helium 2. What changes at this point is the abrupt change in the specific capacity at this lambda point, but there is no energy involved in this lambda transition. And these are nothing but the characteristics of the second order phase transition, which is what is involved in the helium 1 to helium 2 transition. The specific heat is infinite at lambda point, almost infinite at lambda point, and it is called as second order transition. So, one can call it as lambda transition as far as helium specific is concerned, or we can always call it second order transition in this case. So, what we saw just now was what is the first order transition and what is the second order transition. And what we have to understand is the first order transition density changes happen, second order transition Cp or the specific heat abrupt changes are happening. This is what is very specific of helium, and if you understood that, we will go to the next part to understand what is this superfluid helium. Okay. So, this curve is basically giving you the viscosity versus temperature. As I talked to you earlier, the helium 1 to helium 2 phase change, the helium 1 to helium 2 phase transition is basically because there is some viscosity change also. Okay. In addition to viscosity, what has changed was this discontinuity which happened at of Cp at lambda point. But how do I differentiate between helium 1 and helium 2 is basically because of its own viscosity. Okay. Now, here you can see the viscosity, how does it change for helium 1 and helium 2 on the right side of lambda point or on the left side of the lambda point. Kapitsa was a person who did lot of work on helium, low temperature physics and specific to the helium 1 and helium 2 transition. Okay. So, Kapitsa stated that viscosity for flow through thin channels is independent of pressure drop and is only a function of temperature. So, here you can see that viscosity is absolutely constant as far as normal helium was considered. But as soon as you got a superfluid, so we got a normal viscosity associated with this. As soon as you came down below lambda point, the total viscosity decreased drastically. This is what you can see from this figure, all right. How to understand this? This has to be understood that you had very high viscosity up to lambda point and suddenly below the lambda point the viscosity changed. That means you had some different things happening below this. What is this? To explain this one only, a two fluid model is being used. What is this two fluid model? Here I got a different behavior below lambda point. This is my lambda point temperature 2.17 Kelvin, and below 2.17 Kelvin I have got two curves which is giving me the density variations in the superfluid and the normal fluid. In the two fluid model, which is what proposed by Kapitsa, the liquid is assumed to be composed of two fluids, that is a normal fluid and superfluid. So, on the left side of lambda point, what you have got is some normal fluid and some superfluid. As you go on reducing the temperature at 0 Kelvin, what you got is all the superfluid. As you go up to the lambda point, what you got is all the normal fluid. That means, what you have in between the lambda point and 0 Kelvin is a mixture of normal fluid and superfluid, and this is what a two fluid model suggests, that the fluid between the temperatures of lambda point and 0 Kelvin has some density contribution coming from the superfluid and some density contribution coming from the normal fluid, and this is what the two fluid theory is all about. Mathematically, I can write density at any point at this between below 2.17 Kelvin is rho n plus rho s, where rho is the total density and rho n is a normal density and rho s is a superfluid density. So, the total density at any point below 2.17 Kelvin is a contribution from a normal density, that means from the normal helium and from a superfluid helium or a density component coming from the superfluid. So, at any temperature below 2.17 Kelvin, what you have is a contribution coming from normal fluid and contribution coming from superfluid. What you can see from this figure is, as you go below 2.17 Kelvin, rho n by rho, it is a rho n by total density. The density of normal fluid divided by total density is becoming absolutely 0, which means that the contribution of rho n is becoming absolute 0. It is coming to 0, while the rho s by rho starts increasing up below the 2.17 Kelvin and it almost becomes equal to 1, which means that rho s is equal to rho in this case. Same thing is being given over here. At less than temperature of 2.17 Kelvin, the contribution of, as you go down from 2.17 Kelvin towards 0 Kelvin, the contribution of rho s is going to increase given as per this line, while as you go on the right side, the contribution of rho n will start increasing, all right. And at lambda point, what you got is a 100% rho n, or rho is equal to rho n in at the lambda point. The figure shows the temperature dependence of density below the lambda point. What you can see it as temperature equal to 0, you got rho is equal to rho s. That means, it is a 100% contribution of the superfluid in this case. At a temperature more than or equal to 2.17, what you have is a rho n, and between the temperature 0 to 2.17 Kelvin, you got a component coming from normal fluid and coming from superfluid. So, rho in this case is equal to rho n plus rho s. This is a two fluid model which explains to you the total fluid viscosity safely compared to what we see in the viscosity. The superfluid component goes on increasing below 2.17 Kelvin, and therefore, the total viscosity almost reaches 0 at 0 Kelvin, while at lambda point you got all the components in the normal helium, and therefore, rho n contributes to that, and therefore, the normal viscosity will come into picture. If we talk about heat transfer, we just talked about viscosity. The heat transfer in superfluid helium, that is liquid helium 2, is very, very special. When the pressure about liquid helium 1 is reduced by pumping, the fluid boils vigorously. So, if I remove the pressure, the boiling of liquid will happen, of liquid helium 2 will happen. When the pressure above liquid helium 1 is reduced by pumping, the fluid boils vigorously. During pumping, the temperature of the liquid start decreasing. So, I got some liquid helium 1 and I remove the pressure over it. What will happen? The temperature of the liquid will decrease and a part of the liquid is boiled away, all right. But as soon as the temperature of the liquid reaches less than lambda point temperature, that means less than 2.17 Kelvin, the apparent boiling of the fluid stops. That means, what was vigorously boiling earlier, which you could see from outside, suddenly will come to standstill, and a very quiet and apparent boiling which you could see from outside will stop suddenly, which is happening at T less than lambda point temperature. Why does it happen? The liquid now at a temperature less than lambda point temperature, it becomes very clear and quiet, even though it is vaporizing rapidly, all right. So, vaporization is happening, the boiling is happening, however, it has become very clear and quiet and not vigorous as it was when the temperature was above the lambda point. This is difference as soon as in boiling as soon as the liquid comes below the lambda point. Why? It happens because the thermal conductivity of liquid helium 2 is very, very large. It is very large, and that the vapor bubbles do not have time to form within the body of the fluid before the heat is quickly conducted to the surface. Now, this is the real reason what happens below the lambda point temperature. Below the lambda point temperature, the thermal conductivity of helium 2 is so large that before the bubbles reach the surface, which is what happens in normal boiling, heat gets conducted because of this very high thermal conductivity of helium 2. and therefore, because the bubbles do not rise up, that vigorous boiling stops. The liquid apparently looks very quiet and clear, and that is why the word which we had used earlier, that apparent boiling phenomena stops. You can't see boiling happening over there, but boiling is happening. So, you can see from this table how the thermal conductivity changes if one goes from helium 1 to helium 2. You can see here that helium 1 has got thermal conductivity at 0.024 watt per meter Kelvin, while helium 2 has got a 86,500 watts per meter Kelvin thermal conductivity. So, you can see relative difference between these two conductivities easily and can understand why that apparent boiling which I talked about stops as soon as helium 1 goes to helium 2 state below lambda point temperature. Similarly, you can see what happens to the viscosity, which is in minus 10 to the power minus 6, right, in this region, while it has gone to 10 to the power minus 7 to minus 12, depending on the slit size, the viscosity will now show changes. The viscosity will be different for a bulk flow and for a flow through small pipes or small slits. These two property changes of thermal conductivity and viscosity make helium 1 and helium 2 as two different fluids, two complete different fluids, and therefore, their utilities also could be different because of these changes in properties. All right. So, this is what we talked about of helium 1 and helium 2 and also about the phase transition. Just an additional information I want to add to this lecture is that Kapitsa, of which we talked about, he was awarded Nobel Prize in Physics in the year 1978 for his basic inventions and discoveries in the area of low temperature physics. All right. This is what we talked about and its contribution to the superfluidity of the helium. All right. This is my end of lecture, and what you have got is a self-assessment exercise. It was given after this slide. Again, please kindly assess yourself for this lecture very honestly. This will give you feedback about this lecture. These are different questions over here, of which you are expected to answer yourself. I have given the answers also at the end of this. Thank you.